Okay, problem 7.20. Solve these optimization problems. Okay, so we have a lot of different problems that um, ask us to optimize a function, and we have seen that a way to optimize a function is to find a minimum or a maximum. So we have seen that in order to find maximum or stream out functions, we need to find derivatives, right? So this is an application of derivatives, right? So the first part, part A. A factory that produces tomato sauce wants to can it in cylindrical cans. Okay, so let's see. Cylindrical cans, if I can. Okay, of fixed volume V. V. Determine the radius. Okay, so that's radius R and height H, so that their fabrication consumes the least possible material. Okay, so the volume of cylinder like this is pi r squared h. Okay, so the area of the base is multiplied by the height, right? Now, a can like this, it's made of 2 or 3 parts, right? So this is first the kind of straight part, and then the lids, right? This lid and this lid. Now this rectangle has height h and length 2 pi r, which is the perimeter of this radius, and this radio, these circles have radius r, right? So the amount of material that we need to use, assuming that the can has a very finite width, right? So this is almost infinitesimal in width. So the amount of material is going to be proportional to this area, right? So the area of the can is given by 2 pi r times h, and then plus 2 times pi r squared, right? And so this is the area, right? Now we know, because the volume is fixed, we can actually express h as a function of v, right, and r, right? So h is v divided by pr squared, right? So now our function a is 2 pi r times v divided by pi r squared plus 2 pi r squared, or in other words, a is 2v divided by r and plus 2 pi r squared, right? If I haven't made a mistake, right? And now this is the function that we need to minimize in this case, right? So we need to compute the derivative of a with respect to r, which is the only variable here because v is fixed, right? So this is minus 2v over r squared plus 4 pi r equals 0, right? This is one of the maximum, right, or minimum. And so if we can we have this equation, we multiply by r squared, so we have 4 pi r cubed like this, and then r cubed is v divided by 2 pi, or in other words, r is the cubic root of v divided by 2 pi, and h is v divided by wait a minute, it's v divided by pi times the cubic root of v squared pi squared r squared, or in other words, we can rewrite this like this. Sorry, not r squared, it's just 2 squared pi squared, right? And if you operate with this is the cubic root of v, right? Because v divided by v to the 2/3 pi in the denominator, and we have 2 or 4 here, right? 4 pi. Okay, so these are the dimensions of this h, the dimensions of the can that we want. Okay, you could think that this is not a minimum, this is just a maximum, right? But let's see, when r is very small, this is actually how to say it? This is actually negative, right? So the as we keep increasing the radius, right? If r is very small, this is very large, right? So if we keep increasing the radius, the derivative goes from negative to 0 and then to positive, right? So once we reach a critical radius, which is this one, the derivative will increase, and as we increase the radius. So this is actually a minimum. Okay, we can check. Okay, let's go for part B. Part B. A recipient with square bottom, okay, and not cap, no cap. So let's see. It's kind of a box, right? With no cap. So this is no cap. Must be covered by a thin layer of lead. Okay. So we can assume that we just need the area of the lead. Okay. If the volume of the recipient must be 32 liters, okay, so V is 32, L. Sorry, which dimension should it have so that it requires the least possible amount of lead? So again, this is the same thing, right? So the area, well, the volume is, if we call this is a square. Let me forget about the units, okay? You can deal with that if you want. The side of the square at the bottom is L. The height of this box is H. So the volume of this is H times L squared. And the area of this, if you separate this, this is the square, and then you have 4 of them, right? 4 things with height H, right? So we have 4HL plus L squared. Okay. Now with this, we know that V is 32. We can say H is 32 divided by L squared, and in other words, this is 4 times 32, right? 4 times 32, which is this okay? Yes. 4 times 32 is 8 and to 128 divided by L now, right? Plus L squared. And now, just like before, we need to differentiate this with respect to L. This is minus 128 L squared plus 2L equals 0. And so we can write this again, minus 128 plus 2L cubed is 0. So L cubed is equal to 64, implies that L is equal to 4. And H is equal to 32 over 4 squared, which is 16. H is equal to 2. Okay? Okay, so L has to be 4, H has to be 2. And again, we want to check that this is actually minimum, but when L is very small, close to 0, this is super large, negative. As we keep increasing, this gets smaller and smaller, and it gets, this expression goes to 0 when L is 4, and after that it's positive. So this is actually a minimum. C. 5 two numbers, x and y, that are positive such that x plus y is 20 and x squared y cubed is maximum. Okay. So so yeah, let's call a our function x cubed x squared y cubed, and then we want to again express y as well, let's express x in this case. X is 20 minus y, so in this case this is 20 minus y squared times y cubed. So we want the derivative of a with respect to y, and this is 2 times 20 minus y times y cubed plus 3y squared times 20 minus y squared. And then we want to equate that to 0. And so then let's see, we can have common factors here, 20 minus y squared, and then we have 2y plus 320 minus y equals 0. Okay, so let's see, this is 2y plus 60 minus 3y. Yes, and is this correct? Yes. Okay, so 220 minus y cubed 3 y squared. Okay, so everything's correct, right? The derivative of this is yes, yeah, that's the problem. So this is a minus here. Yeah, sorry. So this is minus. Okay, yes. So this thing has three roots. Either y is 20, right, or y is 0, but this we don't care because these are positive numbers. And then 5y is equal to 60, or in other words, y is 12. Okay, so if y is 20, then x is 0, and then we don't want that, right? Because we want those positive numbers to be positive. So we have this solution: x is 8, y is 12. Okay, and then so let me write this better. So this is times 60 minus 5y, right? So this is the derivative of a with respect to y. Let us check that this equilibrium, or this optimum that we have found, is actually maximum of the function a, right? So okay, so start at 0, right? When y is between 0 and 12, which is, let me write this again. So this is 6 times, right, 5 times 12 minus y. Yes. Okay, so if y is positive, then this is positive, and if y is smaller than 12, this is positive and this is positive. So dA dy is greater than 0 if y is between 0 and 12. It's 0 at 12, and then after 12 this is positive, positive, and negative. So dA dy is negative if y is greater than 12 and smaller than 20. Yeah. Okay, so this is a maximum solution, which is what we wanted. And again, this method that we're doing works because all of these functions are continuous in the intervals of interest, right? So we can find all the extrema are found using the derivative. Okay, find the rectangle inscribed in the ellipse x over a squared plus y over b squared equals 1, with its sides parallel to the axis of the ellipse, such that its area is maximum. Okay, so this ellipse, okay, crosses the x-axis at a and crosses the y-axis at b, right? And you can check that this is true. When x is 0 and y is b, this is 1, and when y is 0 and x is a, this is 1, 2, right? So let me see if I can write an ellipse here. Okay, something like that. And now if we inscribe a rectangle here, this is going to be like this. Okay, and you can see that each of these quadrants, this is symmetrical, right? So the area of this is going to be the same as this and this and this. So if we maximize the area of this, we can maximize everything. So let us just restrict ourselves to this this quadrant, right? And we need to maximize the area of this rectangle, right? So if this is our point x and our point y, right? So this is x, y. Now the area is x times y. We need to maximize that. But we know that this point x times y belongs to the ellipse, so we have this restriction. And we can solve, for instance, for y. So we can, y is 1 minus x over a squared, the square root of that, and then b, multiplying this. Okay? So yeah, let's do it like that, or yeah, why not? Or you can express it, you can take a squared out, so you have b over a times the square root of a squared minus x squared, if you want. Okay? And now we can substitute y here, so we have a is x times b over a times square root of a squared minus x. And again, we want to differentiate a with respect to x. And we have the derivative of the first term, which is 1 times the second term plus, and it's going to be minus, right, because the derivative, we have the derivative of the root, which is 2 square root of a squared minus x squared times the derivative of this, but this is minus 2x, and then we have x, so this is minus 2x squared, 2 and 2 go out, and this is multiplied by b and a. Okay, so let me see if I can write this here. And so let's see how we can express this. We have b over a, that's a common factor, and then we take everything under the same a squared minus x squared, right? Same fraction, and so we have a squared minus x squared minus x squared, so this is minus 2x squared, and we want this to be equal to 0. Okay, so this is going to be 0 when a squared is equal to 2x squared, or in other words, that x is equal to a divided by 2, the square root of 2, sorry. Okay, and then if we substitute here, we have that y is equal to b divided by a, and then the square root of a squared minus a over 2, right? A squared over 2, and this is a squared over 2, so the result is a divided by the square root of 2, and so we have that y is b divided by the square root of 2. Okay, so this is the solution, and again we can check that this derivative is negative when x is smaller than this, right? So let me see. When x is small, wait a minute, here. Yes, here, sorry, yes. When x is greater than a, greater than this value, then this is negative, and when this is, wait a minute, this is the area that is maximum. Okay, so the area when x is very small, this is positive, right? So I don't know what's the problem here. Oh yes, yes, sorry, had a brain fart. So when x is very small, the derivative is positive. It reaches 0 when x is equal to a over square root of 2, and when it goes over that, it's negative. So this is a maximum of the function, right? Positive derivative on the left, negative derivative on the right. Sorry about that. Okay. Okay, so let's do part E. We have, with a tangent to the parabola, y equals 6 minus x squared, and the positive axis, we can make a triangle. Okay, so that's true. We can write the tangent here, right? If this was a line, right? This thing and this thing, right? So we have a triangle, sort of, right? So we have y is 6 minus x, right? Determine which of those triangles has the smallest area and compute this area, right? Okay. So the tangent of y at a point, let's call it A, okay, at the point A, is this line. This is the tangent, let's call it A, it's called TA, okay? Just so you, this is the line TA of x, right? Is this line C, let's call it CA, which is the point where it reaches the intercept, right? And plus, and let's call it MA times x. And MA is the derivative of y at A, right? So this is minus 2x at A, so this is minus 2a. So this line is CA minus 2ax. Okay, good. And but now when, let's see, we're, in order to compute CA, right, what's the value of this CA, we have that the value of the tangent at this point A has to be the same of the value here. So this is, it has to be 6 minus a squared. So this is the same as CA minus 2a squared. Or in other words, this says that CA has to be a squared plus 6. Okay, so the tangent at x is a squared plus 6 minus 2ax. Okay, this is my line, right? And now we want our point B, A, to be this point where it reaches 0, right? So TA at BA is equal to 0. Okay, so a squared plus 6 minus 2ab equals 0. And you can solve this, well, this is just, let's see, this is a squared plus 6 divided by 2a. This is b, right? So my equation, yeah, so what I have is the sides, the area, right, of my triangle is CA times BA over 2, right? And CA is a squared plus 6, right? BA is the same, so this is squared, and this is divided by 4a, right? So now let me erase all of this, because we don't need it anymore. We have a formula for the area of the triangle as a function of this point A. We want the derivative of A with respect to A, right? And so we can take the 1/4 out, and this is a squared, and this is the derivative of this, which is 2 times a squared plus 6 times 2a times a, so squared, minus, and then this times the derivative of a, which is a, so a squared plus 6 squared, and this is equal to 1/4. We can take common factor a squared plus 6, and then we have 4a squared minus a squared, 3a squared minus 6 over a squared. And this is going to be equal to 0 whenever this is 0, right? When a squared is equal to 2, or in other words, a is the square root of 2. Okay? And this implies that the area is square root of 2 squared plus 6, which is 8, right? 8 squared times 4 times the square root of 2. Okay, so this is 8 squared 64 divided by 4, which is 16. 16 divided by the square root of 2, or in other words, you can say this is 8 times the square root of 2. Okay, that's the area of the triangle we want. Okay. Now let's go for F. So we want to construct a box with no cap with the shape of a parallelepiped with whose base is an equilateral triangle. Okay, So let me write it like this. Okay. And whose volume is 128 centimeters cubic. If the material for the base costs 0.20 euros, and that for the lateral surfaces costs 0.10 euros per centimeter squared, what are the dimensions of the chip basalt set box? Okay, so the cost here is a function that we want to minimize. It's 0.20 times the area of the basis plus 0.1 times the area of the lateral surface, right? And we are always working in centimeters, so that's fine. So the volume of this is going to be the area of the basis times the height, right? And then we have the area of the lateral surfaces to be, if we call B is the side of the equilateral triangle, this, so let's say AL is going to be 3 times H times B, right? And then we have AB, we can compute the area of this triangle. If this is an equilateral triangle, we know that this is an area, angle of pi over 3 or 60 degrees, and so we have B. We know that this side is going to be B times the cosine of pi over 3, and then this side is going to be B times the sine of pi over 3, right? Now the cosine is square root of 2 over 2, square root of 3 over 2, and the sine of pi over 3 is 1/2. So this is the square root of 3 over 4 times B squared, right? And then now we have 128 divided by the square root of 3 times 4 here over B squared is equal to H. Okay, so we want to express that. And so we have our function C is now, let me express it here, substitute. So this is 0.2, the area of the basis, which is the square root of 3 over 4 times B squared, plus the area of the lateral surfaces, which is 3 times B times this, right? So this is 100, let's see, 100 and, well, let me write it just like V, right? So this is V times 4 divided by the square root of 3 times B squared, right? And now we have our function C as a function of B, the basis of the triangle, and so now we can differentiate it with respect to B, which is what we want. And this is, let's say, well, we can express everything in the same, well, maybe not. So this is 2 times 1.4 divided by 0.1 times the square root of 3 times B, and then we have plus, and then this is B, so right, this is minus, yeah, minus, and then 4 times the square root of 3V over B squared equals 0. We multiply everything by B squared, so we have 0.1, sorry, this is 0.1, so this is 0.12. So 0.1 that multiplies the square root of 3B cubed minus 4 times the square root of 3 V equals 0. Or in other words, the V cube has to be equal to 4 times V. Our V is 4 times the, the cubic root of 4 times 28. But 4 times 28 is, 128 is 2 to the 7, 4 is 2 to the 2, so this is 2 to the 9 over 3, so this is 2 cubed, 8. B is 8 centimeters, okay? And then you can solve using the expression that we had before for H, solve, you had the dimensions, okay? And again, you can see that this is negative for smaller values of b, okay, and then it goes to 0 at 8, and then it grows after that. So this is a minimum minimum cost when b is 8. Okay. Okay, so let's go to G. G is a right triangle ABC has vertex A at the origin, okay, the origin, vertex B on the circumference x minus 1 x squared plus y squared equals 1. So this is the circumference at center 0, 1, and so it does something like this. Okay, so point here B, this is a point A, and then and side A on the horizontal axis. So this is a right angle, and this is a hypotenuse, so this is like this, if I ever learn, and this is C. Okay, so we have this, okay, and this is the right angle. Okay, yes, calculate the location of C that maximizes the area of the triangle. Okay, right, so the area, let's call it S in order surface, in order not to confuse it with A, of this, it's going to be x times y, right, divided by 2, right? But we know that xy here, this point B, xy, is a point on this circumference, right? So we can again solve for y. This is the square root of 1 minus x minus 1 squared, and then we can substitute here, so we have x times the square root of 1 minus the x minus 1 squared over 2, and differentiate this function s with respect to x, and so we have 1/2 of, and let's see, this is the derivative of the first times the second, 1 minus x minus 1 squared, and then we have what, minus, because the derivative of this is going to be minus x, right, times the derivative of this, which is 2x minus 1, but it's going to be just x minus 1 because it's divided by 2 here, 1 minus x minus 1 squared, unless I've made a mistake, right? And then if we want to equate this to, well, this is all equal to multiply by 1/2. We want to equate this to 0, we want to solve this, we multiply this by this, so we want 1 minus x minus 1 squared minus x squared plus x divided by the square root of 1 minus x minus 1 squared, which is always going to be positive in this domain, right? And so x minus 1 squared is x squared minus 2x plus 1, so we have 1 minus 1 goes cancel out, we have minus 2x squared plus 2x plus x plus 3x divided by the square root of something that's positive equals to 0. So that says that this derivative is going to be equal to 0 where x is 0, right, but we don't want that, or x is 3 over 2, right? So it's at this point minimum. Okay, that's what it maximizes the area of this triangle, right? And again, we can see that the derivative is going to be, let's see, this is positive when this is x is very small, right? And then, because you can write this as x times 3 minus 2x, right? So when x is very small, this is positive, and then gets 0 and negative after this grows after. So this is a maximum. Okay. And now let's go for H. H. Let P be a point in the first quadrant, right? Okay. Point X. X0, Y0. This is P. Straight line through P cuts the axis. Okay. Okay. So this is a line that has to go like this. Okay. At this point A, which is x0 plus alpha 0, and B, this is b equal 0, y0 plus beta. Calculate alpha and beta positive numbers, right? So as to minimize, and then three different points, right? So we have the length of this segment AB. So we need to minimize this. Well, let's start with that, okay? So we want to minimize the length of the segment is just x0 plus alpha squared plus y0 plus beta squared, right? And let's see, can we, in order to differentiate or how to say this, yeah, obtain the maximum for this, we need to obtain a relationship between alpha and beta, the two parameters, right, as we have done in every other problem here. Okay, so in order to do that, we need to find some relationship, and there's a hint here. So this says triangle similarity implies beta is equal to x0 times y0 divided by alpha. Okay, how do you get that? Because you have this triangle here, okay, and so we know that let's say this is y0, right? So this is alpha, this is y0, so we have that y0 divided by alpha is equal to beta divided by x0 plus alpha. Okay, and if you sorry, not beta, this is beta plus y0, sorry, beta plus y0, right? So this is beta plus y0. So these two ratios are the same. So if we solve for beta, you have this, right? So now we can express this as this x0 plus alpha squared plus y0 plus x0 y0 over alpha squared. Okay, so we again differentiate this length with respect to alpha. We have 2 x0 plus alpha, right? Plus, and then we have 2 y0 plus x0 y0 alpha, and then the derivative of this, which is minus x0 y0 alpha squared, right? And then let's see, so we want to equate this to 0, and let's see, we can actually rewrite this like this. We can take common factor y0, right, and we can multiply, this is 1 plus x0 over alpha, or in other words alpha plus x0, okay, like that. You can write it like that. So we can have 2 x0 plus alpha, which is a common factor, and we have 1 sorry, this is not minus, this is multiplying that. So this is 1 minus, and you have alpha y0 x0 y0 squared divided by alpha squared. So in other words, yeah, sorry, this is not alpha y0, this is y0 divided by alpha. And so here what you have is not alpha alpha squared, you have alpha cubed. So in order for this to be 0, this implies that alpha cube has to be x0 y0 squared, or in other words that alpha has to be the cubic root of x0 y0 squared. And you can, let me write it here. So for part 1 we have alpha is the cubic root of x0 y0 squared, and beta is the substitute here is x0 yeah, the cubic root of x0 squared y0. Okay, that's the first one. Okay, let me see. The second one is to minimize the sum of the lengths of OA and OB. Okay, so the length here will be OA, which is x0 plus alpha, and then OB, which is y0 plus beta, but beta is x0 y0 over alpha. The derivative of this function is going to be 1 minus x0 y0 over alpha squared. If we want that to be 0, we have that alpha squared is x0 y0, or in other words, alpha is the square root of x0 y0. So for this part 2, we have that alpha is the square root of x0 y0, and you substitute here, you will see that beta is the same, x0 y0. Okay, so depending on what we want to maximize, we will get a different value of this alpha and beta. And finally, the area of the triangle, and let's call it S here. The area of the triangle is x0 plus alpha times beta plus y0 over 2. Okay, but the 2 we don't care, we haven't done this, but the 2 is just a proportionality constant, so we don't really care, and we can substitute beta as y0 plus x0 y0 over alpha, and we know that we can express this like y0 divided by alpha as alpha plus x0, right? So this is x0 plus alpha squared times y0 over alpha, and the derivative of s with respect to alpha is just alpha squared times and then we have, yes, the derivative of this times alpha, so we have 2 y0 alpha x0 plus alpha minus, and then we have this times the derivative of alpha, which is 1, so this is x0 plus alpha squared. And so we have here y0 x0 plus alpha is a common factor. We have 2 times alpha minus x0 minus alpha over alpha squared. And so this is the same as alpha minus x0. In order for this to be 0, these things are always positive, so we need x0 to be alpha. Okay, sorry, not x0 to be alpha. We need alpha to be x0. Alpha to be x0, and so beta has to be y0, right? So yeah, that's it. These are the 3 different values, and that ends this long problem.